Okay, cool. So this is the second part of the tutorial on synthesizing explainable and deceptive behavior on human AI interaction. So before we get into the new topics, I just wanted to set the stage again about all the discussion we had yesterday. And in particular, I wanted to bring up the idea of what it means to do human-aware planning. So unlike the normal, like normal as in the standard planning problems where you have a robot who's or an agent of some kind reasoning about their own model of the task, which is some representation of the task dynamic, their objectives, and so on and so forth. Here we need to reason not just about the agent's model of the world, but the model and the expectation of users it might interact with. In this particular case, in the simplest case, the user or the human it's interacting with is just an observer, but the observer is coming with their own expectations on what the task is, how the robot should act, and stuff like that. So when I say model, I'm generally like focusing on mostly deterministic goal-directed problems. But again, the ideas and the problems here are not restricted to it. It just makes it easier to analyze. And most of the models in these cases, I'll assume, is encoded in this kind of a description language. You can see a snippet on the screen. So that makes it kind of easy to, it's meant to be human readable and something that a domain expert can easily express in. So it's already kind of interpretable, the domain descriptions, provided they are expressed in terms the human understands. So you can see a snippet there about an action called pickup. And the snippet basically says when you can do that action, which is provided by the preconditions, and what happens when you do that action, which is provided by the effects. Okay, so in terms of model, as I was saying, there's a robot model, MR, which the robot uses along with its inferential capabilities, whatever, some planning algorithm or some reasoning algorithm, to come up with what it thinks is the best course of action, pi star MR. Okay, so human, on the other hand, has their own expectations about what the robot model is, which is specified by the symbol MRH, right? And using their own capabilities, they derive what they think is the right course of action, pi star MRH, right? Using this model MRH. So the one of the fundamental problems that can arise here is what happens when the human's expectations about the robot, which is pi star MRH, does not match what the robot thinks should be done, which is basically pi star MR. And especially today, we'll be talking about sorry, how we can address some of those problems. So there are more or less two distinct strategies. One that we saw yesterday, which is let's avoid this entire problem. Let's be explicable to begin with. As in, the robot is not going to do what it thinks is the best, but rather it's going to do whatever it can, which is closest to the human expectation. So there is less confusion. The robot is more or less acting in ways that the human thinks is the right course of action. So there won't be any confusion or questions from the human's part. The other strategy is what we'll call explanations, which is basically let the robot choose to do what it thinks is the optimal strategy to do. And if the human is confused about it, let the agent explain why that course of action is the right thing to do. And by explanation here, I basically am going to focus on answers to questions of the form, why was this plan or policy pi star MR selected? And it could also be a contrastive question. So even the normal why question is an implicit contrastive question, in the sense when the person is asking why was this plan selected, they are implicitly asking why was this plan selected as opposed to any other plans, right? But there could also be explicit contrastive questions where the person asks, why was this plan selected over this other set that I was expecting? Okay, so usually when I'm talking about explanations, I'm mostly focusing on answers to such why questions. And since here the explanations are meant to address this asymmetry in expectation, you can kind of make sense of all these explanations as trying to reconcile this difference in expectations. And um, you can kind of try to categorize these explanations along these three dimensions. One, whether these explanation helps address any knowledge asymmetry between the human and the robot, as in like if there is a difference between what the human thinks is the model of the robot and what the robot thinks is the model of the task. And if there is some such differences to begin with, the human might come up with very different plans from what the robot thinks is the right plan to do. So reconciling these differences is essential for explanation. And the other possibility is the reason why the human expects something different is because their inferential capabilities is fundamentally different from what the robot um, has access to. So, right, the human might think some invalid plan is what needs to be followed, and they are just not getting the fact that the plan they think they expect is invalid, right? So you might also need explanations that address these kind of inferential capability differences. And then the third dimension is about how to effectively perform these explanations, which is basically about vocabulary differences. So what I mean by that is the robot might be fundamentally reasoning about the task in terms that the human cannot understand. So even if in some cases the robot were to, if it was just a problem of model differences, and the robot were to reveal its model information to the human, it may not necessarily make sense to the human because it might be some kind of complex parameterized model that the human cannot make sense of. Like say it's a neural network that encodes the transition probabilities and stuff like that. It wouldn't make sense to the human if you just give the weights of the model to the human, right? So there is also this question of reconciling the vocabulary, or at least translating the explanations or model information or whatever from the robot's end into terms that the human can understand. So there is also the dimension of how do you reconcile model differences when it comes to providing effective explanations. Okay, so this was kind of the dimensions of explanations that we talked about yesterday. And sorry, and what we kind of discussed yesterday was the first dimension, which was about explanations that were purely designed to address knowledge differences. And we basically talked about this framework for explanation called model reconciliation, which basically um, uh, tries to address any possible differences between MR, the robot's model, and the human's expectation of the robot's model, MRH. So we kind of grounded this in this example. I don't know if you guys remember, it was about a simple model where a robot called Fetch, how when is it safe for that robot to move, right? In this case, the human did not know that the robot's hand needs to be tucked and it needs to be crouched before it moves. And this model mismatch could lead to even disastrous results. So model reconciliation was about, okay, we need to resolve these differences. One obvious strategy was, okay, let's just dump the robot's entire model, but that could be kind of unnecessary and also unwieldy and even infeasible in some cases if the robots models are huge. We talked about this idea of minimally complete explanation, which is about, okay, I'm going to give the smallest amount of information about the robot's model that the human did not know, that once they incorporate it into their mental model, can make sense of the model correctly. So in this case, it just meant, so the confusion here was about the robot's optimal plan having this action called tuck. Okay, and the human thought tuck is not necessary; it can just move and there's no need to tuck the hand before it moves. And by saying, okay, this action move has this precondition called hand tuck, you can kind of justify the reason why the tuck action could be part of the plan. So these kind of explanations are found by searching over the space of models. We basically have a search space which is rooted in the human's original model. Then you try to kind of look at what is a minimal amount of information you can incorporate into that model till you get to an updated model that satisfies some condition you had in mind. Which in this case, a model MCEs, which was minimally complete explanation, was that in this updated model, whatever plan that the human was trying to explain is optimal. But that's one form of explanation. There could be weaker things, like you might not want to, you might not be required to justify the optimality of the plan. In some cases, it's just about validity. So that's where we left off yesterday. Before I go into the other dimensions of the explanation, I just wanted to add this one additional information about this kind of a subtlety with model reconciliation explanation, and the fact that sometimes we need to think about this explanation in a larger context, in this case about in terms of longitudinal interaction. So let's assume, right, you have this minimally complete explanation called, okay, the robot model has the action move in robot model has this precondition hand tucked. Let's assume over over future interaction, the human comes to know the fact that the move action also has this precondition called crouched. Now, basically what happens is the original explanation, I'm sorry. The original explanation that robot hand tucked is a precondition of move action, and the plan that was pick up an object, tuck and move is no longer even valid for the human, because in the updated humans model, the action move has this precondition called crouched, and as far as the human is concerned, tucking action doesn't automatically crouch the robot, which is true in the actual robots model, but the human did not know this fact. So after this one update, the human is now won't trust the original explanation. So in these kind of scenarios, such like invalidation of previous explanation could lead to loss of trust and things like that. So in case of like longitudinal interaction, something that might be interesting for the, or might be useful for the system to ensure is, in a sense, ensuring the monotonicity of the explanation. As in, once you give an explanation, regardless of what other information you learn about the robot, it will not invalidate the given explanation. So just to give you a sense of how this, how a monotonic explanation would look like in this case, is instead of just saying, or instead of saying that hand tucked is a precondition for the action move, right? You would say crouched is a precondition for action move, and crouched is an effect of action tuck. Okay, so this makes sure that this is a larger explanation than what was given previously, which was only about one model information. You are now giving two model information. But the good thing is, even if you learn more about, after this explanation one, the plan that includes the tuck action is optimal, because you are doing the tuck action for crouching the robot, right? And the good thing is, later on, if you learn something about the robot model's move action having this precondition called hand tuck, it doesn't invalidate the explanation anymore, right? Because the tuck action, as far as the human is concerned, also tucks the hand. So it all fits in and you don't have to worry about it. I won't go too much into the detail on how the algorithm works in this case, but generally, rather than searching from the human's end, you start the search from the robots model and try to find the longest route towards the human model, where every possible model on the route satisfies the explanation condition. So in that sense, you can think about Okay, so in this case, the purple line are is more or less the longest route from the robot model, where in every possible node in this path, the explanation, the plan is going to be optimal. And then the last model in this path becomes the uh, is the model with respect to which you are generating the explanation. So there you will give enough information so the human's model shifts from MRH to that model. I don't know if you can see it. So it's the, I assume you might not be able to see my pointer, but can you see my, oh, can you see my pointer where it's pointing to? Not sure.
Yes, yes,
Yeah,
perfect.
okay, cool. Yes. So this forms the monotonic explanation in the sense that no matter what additional information you get, right, it's just going to take you to one of these models in this path. So by the virtue of the kind of search you do, every model, the explanation is valid. So any future information, it still holds. The old explanation is going to be valid, and you won't question it. Okay, so that was what we had about monotonic explanation. So one of the things that you might have noticed or may not have, but something that's worth keeping in mind is that the original model reconciliation explanation that we talked about assumes that the system has access to the human's mental model, and the mental model being what the human expects from the robot, as in like what the humans believe about the robot capabilities are, what the robot's objectives are, and so on. And you're calculating this explanation to be provided with respect to that model. So I don't know if you remember from yesterday, there are some cases where this model is going to be known. So some examples where like urban search and rescue scenarios where both the robot and the human starts with the same model. The models diverge over time because the robot has access to information that the human does not. But the robot still knows what the human originally knew. But this doesn't have to be true every time. And the question is, how do we generate explanation when this is not really met, right? So in the next few slides, I'm going to talk about how we can perform model reconciliation explanation when the assumption that the human's mental model is given is not met. So we'll particularly look at two scenarios. The first scenario, you don't know the exact planning model, but you have an access to a set of possible models. And you just know that the human model is one of these sets. Okay, so in this picture, you can see there's a bunch of possible human models, and the robot doesn't know which of this is the actual human model, but one of them, you're assuming that it could be one of these. A natural case where this could be true is when the system has access to what's called as annotated models for what the human believes is true. So here's an example of an annotated model, right? So this is in similar to what we were, the kind of snippet we had shown earlier about this pickup action. But now, in addition to preconditions and effect, there is this additional annotation called possible preconditions and possible effects. And these possible effects and possible preconditions kind of talk about information that may or may not be present in the human's model, and the robot isn't sure about it. So in a sense, we are now dealing with known unknowns, right? There are these possibilities, but you don't know which of them is true. So in this particular example, basically you have two possible annotation, which says there is a possible precondition, a hand empty, and the block being light. What this annotated model is concisely capturing is the fact that the human's model actually is one of these possible four models. One model where none of these annotated preconditions are present, which is, I think, the last one. which is basically the last, the one in the bottom, which basically says there's only two preconditions, clear and on-table. And the non-annotated parts are things that you know for sure. So in this case, the robot knows that the human thinks there is a precondition clear X and on-table X, right? Then you could have a model where both of these things, that the hand empty and light X, are part of the model. So that's one possibility. And then you have the other models where one of these things are part of the model. So in a sense, if there is X possible annotations, you end up with 2 raised to X possible set of actual two models. Okay, so now let's assume you are given such an annotated model. How do we generate model reconciliation explanation? One possibility might be, rather than trying to identify the right model from the set, right? We can try to come up with one set of explanation that works for the entire set, right? So as I was saying, there is 2 raised to n possible models with n. If you are given n annotation, you will try to come up with one set of information that works for all the 2 raised to n. So what that basically means is you take your original model reconciliation search, which was each search node was a single model. And when you apply an update action, like the action you can do in the search was updating that model, and you get a new model. Now each search node is a set of possible models. And when you apply an update action, it updates every model in the set. And basically the first form of explanation, which is called conform in MCE, you're trying to find out the minimal number of information so that you get to a set where your explanation condition, whether it's optimality, validity, or whatever it is, holds in every model in that set. Okay, so this is called conform and explanation. And it might seem at the beginning, this might seem like a extremely complex explanation generation problem. So one of the good things is, even when you have a set of possible models, if you start with the kind of annotated models we were talking about, you can in fact see that you don't have to consider all the models in the set. And in fact, you can just select 2 possible, canonical model out of this set and just do all your tests and search with respect to those 2 models. Again, I won't get into details. If anybody has any questions, we can get more into it. In general, if you guys have questions, feel free to put it in the chat, or if you have access, you are on Zoom, feel free to speak up and I can just stop and try to answer those questions. Okay. One of the things that might be also worth noting is the fact that I assume you guys should be able to see the parallel between giving explanation when there is a set of possible models, right? And the human model is one of those models, versus a case where there is a set of people, right, with different models, and you're trying to come up with an explanation. And you can kind of reuse this idea of conform and explanation there too, and try to say, okay, I'm going to come up with one set of explanation that works for everyone. And there are some reasons why you would want to do that, particularly because when you give the same explanation to everyone, you are in a sense building a common ground. And that's a good thing when it comes to like multi-agent explanation kind of scenarios where you have multiple observers or multiple commanders. It might be worth the effort to build such a common ground whenever possible. So again, this is how we about how this multiple human setting kind of maps into this new annotated model, and then you can use the same mechanism to generate explanation. Okay, so that was the first kind. There are other strategies you can also use in this setting when there are multiple models. One of this is basically you can use these kind of you can kind of use what's called as a um, basically what's called as a contingent kind of planning explanation, where basically the system could ask human questions to resolve its uncertainty. So if only, right, if the robot knew whether or not human knew this piece of information, it might be possible to give a very concise explanation. So in this kind of scenarios, it might be worth providing the agent the capability to ask questions to the human, especially if the human is ready to provide this explanation, this kind of information. So you can think about an interactive version of explanation where the robot asks questions, and based on the information it gathers, it gives a different explanation, right? It's a kind of a conditional explanation where you have these sensing actions from the robot side. You could also have an online or anytime version of the explanation where it just tries to assume an optimistic model for the human, tries to give an explanation, see what happens, and then interact, like over time gives more and more information till the human is satisfied. So that's also another possibility. I won't go into too much details there, but we can talk if anybody's interested about these things. Okay, so that was the first scenario where the robot did not know the actual model, but had access to a set of possible models, one of which was the human's actual model, right? The other possibility is the robot has no information to start with, right? It's like the robot doesn't know anything about the human model, but let's assume the robot has a way to interact with a set of people, right? Collect some data from people with the same background as this user. So in some sense, the robot could put in some effort at the beginning to learn some kind of model, which then it can use for explanation purposes. So one obvious thing might be to just try to learn the actual mental model. But unfortunately, this can be an expensive thing because I don't know if you guys remember from yesterday's discussion, these aren't the mental models of the human about the robot is not the same as the human's own model. It might be true that we might project our own capabilities to the robot or our own beliefs to the robot, but this doesn't always have to be the case, right? So the getting full information about what the human believes the robot's model is could be an expensive process. So instead of doing that, it can kind of try to learn simpler proxy models, which are easier to learn. In particular, we will think about basically a labeling model, which which basically takes some behavior, okay, and in this case we will simplify that behavior as state, action, and the next state, and a set of explanatory messages, right? And we'll ask the human, okay, given this set of explanatory messages, do you think this behavior is explicable or not? And if the human says yes, we'll mark it as 1. If the human says no, we'll mark it as 0. If you guys remember, this is very similar to the kind of models we learned for explicability, where we were trying to figure out what behaviors were inherently explicable to the human. But in this case, we have this additional set of features about what messages would help improve that explicability, right? And once we have this kind of a labeling model learned from all the data set you've collected, and you have a plan at hand, right? You can now basically go back to your model space search, which is now just a search over these explanatory messages. And just to clarify, when I say explanatory messages, they are just basically information about the robot's model. So these information can be generated without having knowledge about what the human's actual beliefs are, right? Because it's just about information about the robot model. And you're going to now search through the space of these messages and see which is the minimal set of messages for which, once given to the human, all the steps in the plan is going to be labeled as explicable. As the human would say, after you get this set of messages, every step in the plan, they would say, okay, it makes sense. So now you are able to, in a sense, recreate your minimally complete explanation kind of search without having access to the actual human model by using this learned proxy model. Okay, so that's the point about how do we perform model reconciliation when we don't have access to the human model. I just noticed that we have some chat. Let me just double check if there are questions or not. Okay. Okay, the question was, in the case where there's a set of possible model is known, can you handle prior information about some being more likely than others? Yes, you can. So basically, what you can think about, generally the original work, the conformant explanation was proposed. We just assumed each model was equally likely. And it did not make much of a difference because basically what the method was guaranteeing was, even if there is a small probability of the human model being something, right, the explanation will work. So it's more or less guaranteeing the probability of explanation being true is 1. But there might be cases where you don't have to quite guarantee it. You can have like a decision theoretic version of this explanation where even if the plan doesn't make complete sense, there is just some penalty, right? So in that case, you can explicitly take into account the probability of these different models being true. And you can kind of try to figure out the set of messages that has the highest expected value. I don't know if given I don't really have access to like some whiteboard, this might at least might be a bit too high level, but the basic answer is yes, you can associate probabilities with each of these possible models, right? And you can, instead of finding a set of messages that is true in all the models, instead what you can do is you can try to find out a set of messages that only works in the most likely models, right? So given this given this particular setting, you are guaranteed that there exists one explanation that will work for everyone, every possible model. The reason why you might not want to do that could be because it's too expensive to give that explanation, because that may be too much information. So by looking at the likelihood of the different models, you can kind of trade off that cost. You can say that, okay, I'm going to use a cheaper explanation if the likelihood of that explanation not working is low, something like that. So you can think about a trade-off of that kind, and associating probabilities with like a non-uniform distribution with a set of models will help you do that. Does that answer the question? Let me know if you need more clarification.
Yeah, it was.
Okay, so hopefully that helped. Let's see. Okay, now we will kind of come back to this idea of there's two different strategies. One is you have this explanation thing where the robot is going to do what is optimal and just decide to give explanation. And the other strategy, which was basically rather than explaining anything, you're going to act in ways the human is expecting you to do. These aren't mutually exclusive strategies, and each has its own strengths and weaknesses. So the thing with explanation is you're going to come up with plans that are optimal to the robot, but the weakness is you have this new overhead of providing this all this communication, right? You have to give this all information at the beginning or something like that. And usually there is a cost associated with both the communicating that information, and now human also has this additional cognitive load of trying to make sense of this information, right? So in many cases, it might make sense to kind of balance these two costs out. That is, combine both explanation and explicable behavior generation strategies. And this is what we will call as balancing. So I'll just kind of motivate this idea of balancing in this urban search and rescue scenario, where the robot needs to go from one room to another, and there are certain corridors that are blocked due to rubble. And the corridors the human thinks are blocked are not necessarily the ones that are really blocked in the world, okay, or in the building that the robot has better access to. And in this video, basically, this is like a demo video we made in the ASU lab. You can kind of see right now the robot is doing purely explanation scenario, where the robot has to give multiple information. One about, okay, the path you thought the human thought was best was blocked. And then it has to also talk about why the path the robot is going to choose is actually safe to use because it doesn't have these kind of debris and stuff like that. So in this case, in this particular case, I'll just pause it for a second. The explicable plan, the plan that the human expects the robot to do, is actually infeasible, right? Because the path is actually blocked. But instead, there is this middle way that the robot can choose to do, where the robot gives just a single explanation, which says what the human was expecting is blocked, and then not worry about explaining more so that it has to justify its plan, but rather take a suboptimal path in the robot's model, but which requires less explanations with respect to the human's current model. So in this case, it will take a slightly more costlier path where it's clearing all this rubble before it can move. But this path only requires a single explanation as far as the robot is concerned to the human. Okay, so this is what I'm referring to as balancing. So it's in fact balancing any loss in optimality by taking paths that are more explicable to the human with respect to any costs that are associated with explanation. In fact, the most general version of balancing, you can kind of think of it as being this multi-objective planning problem, where you are balancing between the cost of the plan itself that the robot has to execute, the cost of the explanation, and then the cost of like any inexplicability. As in, maybe the robot doesn't want to ensure that the plan is completely explainable to the human, but there might be some amount of like inexplicability, but that's okay, right? There is maybe some penalty associated with it, but it might be a penalty that is worth for the robot to kind of pay for, provided it saves a lot in terms of communication or the cost of the plan it has to execute and so on. So in the most general cases, like a multi-objective planning problem, you could turn it into a single objective by just combining these different cost terms. So in general, in fact, when you turn it into a single objective planning problem, there exists a way to kind of compile this planning problem, like a single objective planning problem, into a classical planning problem by creating this new augmented model where the system is not only reasoning about the effects of its action in its own model, but also the effects of an action on the human's belief. And you can actually model the explanations itself, right? The various information it can give. as just another set of actions the robot can use, which is called as explanatory actions. And you can turn the whole thing into this one huge planning problem, give it to a planner, and the planner can reason about both explanation and what actions to do. So it just turns into the single planning problem. I won't go too much into the details on the planning compilation itself, how that planning problem is formed. But if people have specific questions, I can get to it. But this is just like details on the exact the planning formalism. But if anybody is interested, and if people are aware of things like epistemic planning, which is planning about other agents' beliefs and how their actions might affect beliefs, this is basically building on works on that thread. Basically, you're turning this explanation problem into an epistemic reasoning problem, where explanation are basically actions that have epistemic effects in the sense that they are updating the human's beliefs. Okay, so that brings us to the end of all the explanations related to the first dimension of like asymmetry, which was asymmetry in knowledge. And the next dimension is asymmetry in inferential capabilities. But before I get into it, I just wanted to check if anybody had any questions. Okay, I see we don't have any chat as far as I can see. So I'll just get directly into it. But again, feel free to put the questions, and if I don't see it right away, I'll try to get back as soon as we get like a natural break in the discussion, and we can go over the details. So let's assume for now, the human has access to the true model of the robot, right? The human knows everything the robot knows, and the capabilities the human ascribe to the robot is the same as the capabilities the robot actually has access to. But even in these cases, the robot behavior might be confusing to the human if humans' ability to reason about the model is in some ways limited, right? Because the problem itself could be so complex, and the state-of-the-art planners you have access to are really powerful. So the planner might be able to come up with long, complex plans that makes no sense to most of the humans, right? So even if they knew everything, and if they were the domain expert, they might not have thought about the same solution, right? And this is basically the next dimension of explanation that we'll focus on. How do we address this mismatch in inferential capabilities? How do we explain to the human that the robot's actions make sense when the human is in somehow limited in their reasoning capabilities? In the works we are going to talk about, we'll just mostly focus on 3 strategies. The first one is what is basically, we will allow for more interaction from the human side. That is, the human can ask more questions. Right? They can be more specific about, okay, why didn't you do this? Or why did you do this? Or something like that. Which means the robot can provide more targeted information and also provide other additional information that could help make sense of the plans at hand. The other possibility is the robot could use abstractions. As in the task model itself that the robot has access to could be quite complex. But most of those information may be relevant to the current task at hand or current objective at hand, or also most relevant to the specific question that they are asking, the human is asking. Right? The human might only be interested in some part of the plan, or they might have some question about why this strategy was selected over another. And to answer that, you might not have to take into account all the details. So you can use some form of abstraction to, like, remove a lot of details. So making it easier for people to understand. The other related concept is you can take the whole problem and kind of decompose it into smaller problems and then explain with respect to the smaller problems. Okay. in terms of the first strategy, sorry, um, allowing for more interaction. The specific strategy we will talk about is one where we will allow the human to raise foils. Where foils is something that comes from explanation literature, the larger explanation literature that's not just for XAI, but in terms of psychology and stuff like that. And what they've noted is people generally expect what's known as contrastive queries. And basically contrastive, not queries, contrastive explanation, in the sense that people generally expect, even when they ask a why question, right? Why this plan? They usually have an alternative event or alternative decision they had in mind. So even when they ask why P, usually the question they have in mind is why P and not Q, right? P being the event that needs to be explained. And as such, the explanation they have to receive has to somehow contrast why P happened or why P was selected over this Q. And this alternate they had in mind is what's usually referred to as foil in explanation literature. So in this case, we'll specifically allow human to ask these kind of explicit contrastive queries where they will ask, okay, why did you select the human last agent? Why did you select the specific plan pi star MR instead of these other plans that I was expecting, which was pi 1, pi 2, or whatever, how many ever possible plans. And what that allows us to do is you can give much less set of information. You don't have to ensure that the plan that you are trying to explain, the agent is trying to explain, is optimal. Rather, you have to only ensure that the plan is better than the alternatives that the human came up with, right? And that might be a much simpler, might require much less information. The other thing is you can now, if you have the exact question that the human, the exact alternate plan the human had in mind, you can now give additional information that might make it easier for people to make sense of the explanation. So in addition to model information, given this updated model, you can kind of walk the person through as to why the alternatives they had in mind may either be invalid, right? At some point, maybe the alternatives they had in mind might fail, or why that might result in more cost than what the robot was trying to do, and things like that. So you can give these additional information that will make it easier for people to make sense of it. Okay, but this isn't a foolproof thing. There's a bit of a catch. One is, one is the humans are, most users are rarely ever going to give you the exact alternative they had in mind, either because it's going to be costly or maybe they hadn't completely thought through. In most cases, they might say, okay, out of this entire plan, why did you not, they'll see an entire plan and they see the robot is picking up a block, some specific block. Let's say it's a red block. The robot is picking up a red block. And the human might ask, okay, why did you pick up the red block and not green block? And what that question is implicitly asking is, why did you pick up this plan opposed to any other plan where instead of that red block pickup, there is a green block pickup? But the rest of the plan could be extremely different, right? So what this end up happening is you have a set of foils that is pretty large, right? In some cases, the best way to represent these kind of foils is not as explicit plan sets, but rather as a constraint planning problem. And now you are back into the same problem of you have to either show why this constraint planning problem may be unsolvable, in that once you pick up the green block, there can be no valid solution, or the best solution that's going to come out of this constraint planning problem, that is any plan that involves picking up the green block, is going to be worse off than the current plan, right? So now you're talking about still giving explanation at the level of entire planning problems. So it's still going to be kind of expensive. And it's not as simple as when the people might have provided like explicit plans as their alternatives they had in mind. Okay, now the next strategy, so now that's a foil strategy. The next strategy that you could employ is abstraction, right? As I was talking earlier, when the agent is trying to explain a given decision, right, or even trying to provide an explanation that contrasts the given decisions to some alternative, even incomplete alternative, like the way we are talking about, it's a constraint. It's possible that the agent doesn't have to consider all the information in the model. To kind of ground that, let's just look at this simple rover example, right? This is rover domain where like this is like a Mars rover, right? So Mars rovers are complex systems which has a lot of different goals and tasks and stuff like that. It may need to go from one point to another. It might have to collect different kinds of samples, like it has to collect soil samples, has to collect rock samples, it has to measure the sunlight, weather, so many different things. So these task model of this robot could be extremely complex. But if the person just wants to understand why in this particular setting, this rover can't go from its current position to that green cell, right? It's just us trying to understand that specific part. Most of those information is irrelevant. You don't have to talk about why where the different soil samples are, what the wind speed is, what the current temperature is. Most of those information is actually unnecessary because it can't get to that green cell because the path to the green cell is blocked by rocks. So in a sense, you can ignore most of the details of the problem when you're trying to explain why it couldn't get to the green cell. Right? And this is something we do naturally in our everyday explanation, right? When you ask me some questions, I don't give you all the information about my life, but rather just the information that is relevant to the current question. And this is an intuition we can also apply in explanations for whether it's sequential decisions, plans, single shot decisions, whatever it is, right? We can just talk about things that are relevant to the question at hand. And one way to kind of, especially when you have models of the kind that we are interested in, like all the PDDL style problem, one can kind of create these kind of models automatically by doing these kind of syntactic operations. So the one kind of thing is like, if you want to just project out this information about rocks, you can just take that a description about the action and just remove that information from the action. So now you'll get a much simpler model that allows for more solutions. And then you can talk in terms of those solutions and those models and stuff like that. I won't get into too much details, but again, happy to talk more in case people are interested about these kind of things. Okay, so basically what this turns into is there is still going to be a search for explanations here, but now instead of searching over model updates, you're just searching over different kinds of abstractions, and you're going to try to find the minimal abstraction where you can give the explanation. And you can, even this case, you can kind of think about model reconciliation, one where human, in addition to being a kind of a way to improve like the inferential capabilities, you can also think of it as being a model reconciliation because you're still exposing model information, albeit in in abstract form, so it's easier for people to understand. So you can still kind of think of it as a special case of explanation. So I just saw a question that just came up. Let me just check what the. Let me stop the video. What is the question? Okay. Could foils be used as well as ways to refine the problem specification further? Yes, in fact, you can. So I'll just read the full question. And in fact, I'll just run this video too, because that's kind of getting to the point you was asking. So the question was, could foils be used as well as ways to refine problem specification with further instruction? Why did you turn right? That would be much costlier, but you could pick up a red block on your way right. I had to pick up a, okay. So this is slightly different in the sense of you're using foils as a way to get more information from the human in terms of like what the human had in mind. Again, that's something that we will see in one of the applications. Hopefully I'll have time to get there, but whoever asked the question, they are completely right. In a sense, when a person asks a question like this, it's not only revealing their like maybe limitations about their inferential capabilities, it might also be revealing some hidden preferences or some hidden specification that was not specified earlier, especially in a setting where the person was also the one who had specified the robot objectives and stuff like that. So when they were asking a question, it could be an implicit evidence that they might have had some preferences that was not revealed earlier. So we will specifically see a system called RadarX, which does exactly this. But yeah, but I think might make more sense to talk about it in that particular setting. So this video was specifically not about that. This was about how the kind of question you can ask allows you to decide the level of detail at which you can kind of give explanation. So this was about two kinds of question. One was there is a naive user, which is just like a normal everyday user of the robot who's asking this question of why didn't the robot pick up, like there's, if I had ran the full video, you could have seen that the robot was trying to pick up a jar and say, I can't put the jar on the shelf. Can you put it? And the human would ask, okay, why didn't you put the jar? And it'll give a very high level explanation like, okay, I can't reach the shelf or something like that. But on the other hand, if you were like an expert, like a roboticist, they may ask more detailed question like, okay, rather than saying, why didn't you put the jar on the shelf? It might ask something like, okay, use this specific grasping angle and try to put it in the shelf. And by the virtue of the fact that it's asking such a specific question, you can actually go down in the level of abstraction, as in like go to a more detailed model, use that detailed model to generate explanation. And you can give additional debugging information like you could show simulations and stuff like that, which would make more sense for a roboticist than like a naive user. So you can kind of use the level of details used in the question itself to kind of figure out what explanation to give. But yeah, this specific question we'll get back to as part of the application. Okay, so that was about abstraction. The next part is about problem decomposition. So even in this case of why did the rover not go to the green cell, you don't have to talk about the entire planning problem. That is like, you don't have to talk about the entire problem of the robot starting from its current cell and making its way to the green cell. You can talk about breaking this problem down into smaller problems. And one natural way for breaking down problems for planning would be to talk about sub-goals, right? So one sub-goal is before getting to the green cell, you might have to get to this red cell. And look, I can't even get to this red cell because there are rocks on the red cell, right? So now it's a much smaller planning horizon. It's a much simpler problem, right? And it might be easier to talk to the person in terms of those. And one useful technique that people have looked at in the literature to kind of generate these kind of problem decomposition is something called as landmarks. It's basically, in some sense, some state facts or some logical formula that has to be satisfied by every valid plan. That is, every plan that goes from initial state to goal would have achieved this landmark at some point. So you can kind of think about them as sub-goals, because no matter what you do, you have to first get there before getting to the goal. Again, given the lack of time, I won't go too much detail into this, but there are some subtleties, right? Like if you're explaining unsolvability or something like that, there won't be landmarks. So you might have to first relax the problem further to kind of even generate landmarks. And landmarks have also been kind of used to summarize policies. So if you know of MDPs, when it's like stochastic problems, you can't just talk about solutions being like a single sequence of actions. You have to talk about all these possible eventualities. Okay, if I do this action, this happens, then I have to do this and this. So just communicating all this policy could be an extremely complex thing. So this is just like the graph you're seeing, the black and red graph is just a policy where all the red dots are the states and the black edges are all the actions you have to do. And so it's like a bushy kind of complex thing. But rather than talking about all the eventualities, you can just kind of talk about, okay, regardless of what actual path I end up taking to the goal, here are all these intermediate sub goals I have to get to. And that kind of helps you summarize the policy. And that can be the basis of the dialogue. Okay, you can start with this summarized version, and then you can kind of go back and forth. Okay, so again, we kind of, we're still at part one. So the last thing I'll kind of quickly go over is the fact that what if you have this, whether it's model differences or inferential differences, but the robot's model is in a form that just doesn't make sense to the person, right? It could be a learned neural network. The whole transition probabilities is just a huge parameterized neural network, and you can, it's not like you can just give them that neural network weights and expect people to make sense of it, right? Because people generally think of world in terms of objects, relationship between objects and things like that. So just dumping this network might not be quite helpful. So one thing you can actually do is you can still use all of the techniques I talked about, but you have this additional process, this initial pre-processing step where it might take the model it has and translate it into terms that the human understands first. Well, basically what the human does is they will give a set of concepts they understand about the task, and then you'll try to map your modeling, the agent's model information into those terms. So one way to operationalize this might be to learn a set of classifiers over states about the various concepts that the human thinks are relevant to the task, and then try to build a symbolic representation over these concepts. And usually, let's assume the system has some model or a simulator, and you can use some kind of sampling algorithm to kind of learn this kind of things. So one of the things to keep in mind, one of the challenges to keep in mind is, one, you're going to use a sampling-based method to learn this model. The second, all the mappings, that the concepts that the user gives and the mapping you learn over those concepts could be incomplete and noisy. So there is a probability that the model you learn, this approximate post-hoc symbolic model you learn, might not be actually accurate. So it might be worth making the effort to quantify the agent's uncertainty over these learned models, and only provide explanations if that uncertainty is over a certain limit. The system could also surface this uncertainty to the human. You can say, okay, I believe with confidence 80% or whatever, or like probability 0.8, that the reason why the question you asked. So let's say the person asked, the question was, try out this another plan. And you would say, okay, with the probability 0.8, if I try the plan that you are asking me to do, it would fail because you wouldn't satisfy this precondition I have. This precondition would be some symbolic information that was learned post-hoc and given to the human. Okay, so that kind of wraps up the part about explanation. And I still am hoping that I can quickly go over the deceptive behavior and some of the, like at least two specific applications of the kind of techniques we've been talking about over 2 days. So it'll be a little more high level because I don't think we have enough time. But again, people have questions. I can try to stop and then try to drill down further. So first off, we've been talking about explanations, explicability, being cooperative, being transparent, being legible, things like that, right? So these are all things that you would want from an agent. But it's also worth keeping in mind that most of the techniques we've talked about could also be used for adversarial purposes and for deceptive purposes. And in some cases, these kind of deception and adversarial behavior may be required. Maybe it's a property of the problem, or maybe it's for the greater good. I'll talk about an example where it might make more sense to lie rather than provide explanation. So in some sense, we might have to provide white lies, right? So one possible scenario where we might have to be kind of deceptive, or we might have to do something that is not as transparent as cases where the system has to obfuscate some information, right? Let's say there is some third-party attacker or somebody who's trying to snoop in to the robot's behavior, right? It might be somebody trying to steal some proprietary information or something like that. And it might be worth going to the effort to be obfuscatory in its behavior, to kind of withhold information about what it's doing, why it's trying to do what it's doing, and stuff like that. So if you guys remember, yesterday I was talking about legibility, and predictability, and this is kind of like the inverse of that problem. Legibility was about trying to reduce the human's uncertainty about some information, right? Which in this case was like legibility's case was goal, and obfuscation is the exact opposite. You're trying to increase the human's uncertainty, or trying to maintain the human's uncertainty over some information like goal or something like that. And this is particularly interesting when you have things like partial observability. That is, the human can't see exactly what's going on. They might be able to see some observation, try to infer what the actual behavior was from that observation, right? And by being clever in the kind of behavior you do, by taking into account the kind of observation that could be emitted, you can be very obfuscatory in terms of what a human could get. So just to kind of ground that, here's a simple urban search and rescue scenario where the robot has to robot has to both go to a room and survey it, and the room is given by that red kind of light thing. So the robot has to go to the room and survey it, and also has to go and help one of those victims. There are two victims, right? And the human doesn't know which of the victims they're trying to save. And maybe the human is trying to find that out to somehow stop the robot or something like that. And let's say it's a partially observable scenario, because like an urban search and rescue scenario, and they can't really see everything that's going on. And the only thing they can see is what is when the robot does the survey thing. As in, like, when the robot enters the room with that red light, the human can kind of find out, but the human cannot figure out when the robot does the triage operation. So one of the things is, if the robot were to go to that room in the first step, as opposed to going to the room in the fifth step, right? In first step, it's still possible that after it does the survey, it might either go back to the victim on the bottom row, or it could go to the victim on the top row, right? So there's still some uncertainty. But if the robot is entering the room in, like, say, the fifth step, there's more likelihood that the robot must have already performed triage, or like try to help the person in the lower rows, right? So it gives you some information about what the human might be, the robot might have been trying to do. So this is kind of an obfuscation in case where it's trying to maintain some uncertainty by acting in ways that's kind of harder for people to get a sense of. Okay. So that's about obfuscation, and there is an like an analogous obfuscation strategy also in the case of behaviors itself. We can try to hide its behavior, particularly when it comes to partial observability. This can be, there are effective ways of doing it, right? And then there is the deception, where it's basically trying to in a sense, it's related to obfuscation, but in most of the cases, you're not just trying to be reduce uncertainty. You might also try to fool the human to thinking that the agent's goal is something else, and things like that. So usually the literature, I'll like especially talk about two techniques. One is called simulation, where the robot is going to select an alternate dummy goal. Okay. And then it's going to act at the beginning as if it's going towards the dummy goal, right? And once it gets to dummy goal, it's just going to go straight towards the actual goal. So up to the dummy goal, the human observer would think, oh, it's going to this dummy goal. So in a sense, the human might be fooled into thinking, okay, that must be the goal the robot is trying to do. And this is usually called as a simulation. And there is this other method called dissimulation, where you, again, the system selects a dummy goal and then tries to find what's called as a target node within the planning space. And like, let's say in this case, it's a cell, right? That's a cell where if you, from that cell, the likelihood of going to either of these two possible goals is equal. And the agent is going to like directly take the shortest path to that node. So when you, once it gets there, the human is still confused which is exactly it's trying to achieve. And from the target node, it'll just go to the final goal at the end, right? There is a different version of dissimulation where it not only goes to the target cell, but rather it's going to take paths that actually favor the dummy goal over the other one. So it's not only going to be confused when it reaches the target node, but on its way, the human might think, okay, the dummy goal is more likely. And there is a more stronger version of it where you actually avoid taking any intermediate paths, where the human might think the path to the actual goal is more likely. So you're actually going to like prune out, avoid even going to those kind of states, and just take this route to this target node, which makes it seem like you always want to get to the dummy goal. And once you get to the target node, you're going to shoot your way to the actual goal. So this is what's called as deception. And then there is a question of lies. So in an adversarial setting, lies makes a lot of sense, right? You just want to just give the wrong information. So one way of thinking about lies, like I was saying, obfuscation is kind of like your symmetric image of legibility. Lies is in some ways symmetric image of explanation, right? Particularly the model reconciliation kind, where you're giving out information as if they are true facts about the robot or the world, but those informations are not true. So you are kind of giving out false information. So in the case of adversarial things, that makes a lot of sense because, yeah, you just want to fool the person. But even in the case of cooperative things, sometimes it makes sense to talk about or use lies in a sense, because sometimes it's easier to lie than give an accurate explanation. So again, I won't go too much into detail about this particular example, but this is an example where this is the current human mental model, and the robot is going to choose this rather convoluted path, when the human thinks, oh, the robot could have just taken the ladder to the swimming pool. Let's say the goal is the robot to get to the swimming pool. It should have just taken the ladder, which is on this end. Let's see if you can see the explicable plan. This is what the human expects the robot should do. But rather, the robot is doing this. And the reason why it's doing this is because this is the actual model. There are all of these different obstacles it needs to avoid. Like there are all these things that are blocking the path. And the thing is, here, even an explanation towards why that path is not possible, right, is actually quite expensive, because you have to talk about these two different places being blocked and so on, so forth. So here the explanation is kind of expensive. And one way you can avoid it is just to give them a lie, right? And literature has kind of looked at especially two kinds of lies. One is what's called as a lie of omission, where the robot might say something is false, right? And when it's not. And lie of commission, it will just come up with an imaginary fact, right? It might just come up with something that's not actually true. And just to kind of give you an example of lie of omission, it could say, okay, that ladder is not actually there, or like there is no clear ladder. That's a lie of omission, because you're just saying some fact is not true. And like a lie of commission might be to say, okay, there is actual rubbles there, like you're inventing new facts about the world and then putting it. So one of the interesting things here is actually lies in some sense are harder to generate than explanation, because you have to be creative in a sense, right? Because you have to think about lie of omissions is less hard, because you're just trying to remove facts. So you know all the set of possible facts that are true, and they're just going to say some things are false. But lie of commissions are hard because you have to be creative and you have to come up with possibilities. In a sense, that's like an infinite search space, right? Like the model reconciliation search we've been talking about is limited because you are only need to talk about things that are true in the robot model. And lying requires more creativity, and it's usually a harder computational problem. And one could even make the case that that is true in real world too, right? Like in our human everyday life, lying is a creative process. You have to think about, oh, what are all the possible worlds that you can talk about, and which of the worlds are more likely than others. So those kind of intuition also carry over when it comes to lying from the perspective of the robot. It has to be creative. It has to talk about what is a more plausible lie than another. And these requires additional mechanisms, which makes the process a hard process. Okay, so we are getting to the more or less the end of the thing, and I just wanted to take a few more some time to kind of talk about some of the application. Specifically, there are a few multiple applications that we could have talked about, and the original EEI 20 tutorial has a bit more longer application section that you can kind of go over to get the sense of the space of all the things. But I just wanted to take the moment specifically to talk about two things. One is what's basically the problem of collaborative decision making. This is the case where you have, this is the problem faced by something like NASA mission controller, right? Or where there is a domain expert who's trying to come up with a plan, and you have this assistant who's trying to help speed up the process. So the domain expert is the one who knows the problem completely and knows all the information. And this, or it could also be the case that the assistant is keeping track of multiple data sources, are collecting different things to speed up the thing. So there might be cases where the assistant knows more about the world than the agent, the commander. But in generally, the commander makes the last call on what is the right plan to do and right action to do. So here, the way assistant can help things. So this is basically a system that was developed in our lab in ASU called Radar, which was basically designed around the simulated, disaster recovery scenario, where you had a commander trying, like a firefighter who's trying to come up with a plan to combat a fire that was happening in a city. And the kind of capabilities that the system provide are things like the commander can drag and come up with plans, which is like a sequence of action, and the system would in real time talk about, oh, this plan is not going to work because there is this error. Let's try to validate things. The commander could ask for completions, right? Where the commander will basically say, okay, here are some of the actions I want, fill in the rest, right? So it can ask for completions, it can ask for suggestions, right? Like come up with a plan for me. And it might ask for explanations for those suggestions, right? Like, okay, why did you give me the suggestions and things like that. So an interesting point here was, like I was saying, the agent might have access to information that the commander does not. So model reconciliation is still quite useful here. So it can, at the beginning, both the robot and the commander has the same set of information, which could be the map of the city and stuff like that. But because the agent is keeping track of these different, maybe different news sources and stuff like that, it might have more up-to-date information. And it could use that to kind of give an explanation. So in this case, there was an explanation that says, it was basically, I think this model explanation is about two preconditions, right? Like it's saying, okay, I have to, the reason I chose this particular plan is because there are these preconditions, this model update that you weren't aware of. But because the commander is the one who makes the last call, here in this scenario, they can choose to override the system. They can say, okay, I accept the fact that to deploy big engines, there has to be some kind of alert. So that's basically, let's say that's what the first line of the explanation says. But I disagree that you need to have an alert to deploy rescuers. I can deploy rescuers without even having seen an alert, right? So here the commander pushes back on the explanation. And what the system does is it takes this updated information, updates its own model, okay, and then updates the suggestions and the plans it would have come up with. So it becomes like an iterative process. The suggestion, the user gives new suggestions and updates it. There's also a case where there are multiple commanders. These different commanders have different views, and now the thing we talk about conformant explanations with multiple users, we use that kind of techniques here to kind of support multiple users. And we also had like a HoloLens mixed reality view where different commanders were shown different information and stuff like that. There was also the system that was implemented. The same system was implemented for like a plan of study thing, like in a sample system where the student had to come up with a plan of study, and this was validated through a user study and things like that. So I wanted to specifically bring up this particular extension because that kind of connects to the question there that was asked in the chat, as I understand it, which was basically these foils that the person asks is in some ways giving you some information about what they wanted, right? I think in that specific example, the human was just saying, okay, can you still pick up a red block on your way, right? Usually, it doesn't have to be that clear cut. Okay, so the person asks, okay, do X, Y, Z, which is pick up the red block, pick up something else, and then do this, right? And it's somehow reflecting what they would have wanted to see. And maybe the system can't do it because that particular sequence of actions cannot be done because of some hard constraint, right? But that doesn't mean that we should completely throw away that recommendation or that question. Maybe there is some part of it we could salvage, and that would still be good for the commander. So in a sense, after you give an explanation, so they ask for this foil, which was basically pick up a red block, pick up a green block, and put it in the safe. And you will give an explanation that, okay, I can't do all of it because of the fact that I can't hold a red block and green block at the same time, right? So that's an explanation why it can't do it. And instead, right, not instead, like after you provide the explanation, now you can give more info, like you can now try to get as close to that suggestion as possible. So in the robot could say, okay, here is the explanation why I can't do what you're asking me to do, but would it be okay if I pick up the red block, put it in safe, then come back and pick up the green block and put it in safe? So now you're talking about after the person asks the question, you're coming up with the closest possible plan that you can do that is close to what the human was asking. Or after you give the explanation, the robot could ask, okay, what you are asking me to do is kind of impossible, but do you care about picking up red block more than picking up green block? So should I select between these two ones? So now you're giving the person the choice to kind of ask the like more probing questions or give more information so the robot can kind of, update its behavior. In this particular case, it's not a robot, it's about the suggestions because it's the suggestion given to the commander. So you can kind of give those information. Okay, I think we've mostly run out of time, but the second kind of thing was an application where rather than the model reconciliation one, it was more focused on the inferential ones. And this was implemented in this system developed by IBM, which was about an interface which was meant to acquire models from humans, which allowed people to specify this was for like conversational bots. So usually in enterprise settings, conversational bot, somebody is responsible for writing the script for it, right? It's still the AI is kind of limited. So somebody writes a script for it. And usually the scripts are like extremely big trees and it's a kind of a painful process. So the system they had come up with was, okay, I'm going to basically create this system, this interface that allow people to give declarative information, which is basically kind of specifying a domain model, like the kind of planning models we've been talking about. And the planning model will be used to create this dialogue trees. Okay, so what they ended up seeing, I will just skip all this information. What they ended up seeing is this was a good step, but this was still kind of limited because people, once they give these kind of declarative models, the outputs don't always match what they were expecting. They would have, maybe it's because they made a mistake, or maybe because they couldn't see something about the model they had made, and it's kind of what's coming out doesn't make sense. Many of the times there's no solution, and they say, well, they can't kind of figure out what's going on. Right? You can kind of think about the problem here being like there's an inferential limitation, and all of the things we talked about, all three techniques we talked about was implemented here. We looked at coming up with abstractions where the question they were asking, like, why is this not solvable? Okay, let's find the most abstract model which is still unsolvable. And then the person can debug that model. Or if there is an alternate solution they would expect it, you can ask the foils, right? Like, and you'll still talk about finding the abstraction where that foil is possible. And you can talk also figure out about talking about landmarks, which is like sub-goal stuff. You can say, okay, there is no solution for this because I can't get to this sub-goal, which is in this case, there is this handoff of user initiative that was not happening. So you can kind of use that. Okay, so this makes it much simpler because now people aren't dealing with full models. They're not dealing with full conversation trees. They are working with abstract ones. And that was kind of the kind of applications we looked at. Okay, now that we are at the end of the talk, I just wanted to flash the slide again. Hopefully that we saw last time as to where we would want intelligent agents to be. Right? We started from the intelligent agent architecture, which most people are familiar with. This is like the textbook version of it, where you have an agent working in a world, but where we would want our systems to be, especially if we want systems that are explainable, right? That are able to work fluently and work effectively with people. We want systems that are capable of reasoning with humans models and stuff like that. So this is where we want to reach, and at least this is our proposal of how do we, one of the core requirements for building these kind of systems. Okay, so that brings us close to the thing. And there is one more question here. How do I at least you position your work with respect to case-based reasoning and evolutionary rule-based recommendation approaches? So they are all useful. Like I think rather than the specific techniques, right? I think the case I'm pushing for here, or at least the case that was being pushed both in the earlier tutorials, is rather than the specific techniques you use, the system has to, in some sense, make use of the fact that, or keep in mind the fact that it's going to be interacting with people, and it's going to have to keep in track of their beliefs, the humans' beliefs, humans' limitations when it comes up with the interaction strategies. So I'm not as familiar with evolutionarily rule-based recommendation approaches, but for case-based reasoning, right? That's a good example of one case where you can kind of use, at least in the case of explanation, the case-based explanation, you could kind of, let's say you're explaining a decision, right? You can say, okay, this decision is similar to these examples, right? So in some sense, it is an implicit way of agreeing to the fact that humans have limited inferential capabilities. The real explanation, as like one dumb way of explaining things would have been, here is my entire neural network, okay? Make sense of it. But rather you are allowing for the fact that humans have limited inferential capabilities, and maybe this example-based approach, where you are giving these cases and trying to explain with respect to it, is an effective way of doing it, right? So this is you are making an allowance for humans' inferential capabilities, but most of the time we do it implicitly. We are making this implicit assumption. So even in case-based research, originally, I think a lot of this was kind of, there are psychology roots for many of this. So in a sense, maybe case-based reasoning based explanations is in some ways allowing for the fact that the humans think in terms of examples, and maybe examples are a good way to provide these kind of like help the humans reasoning process. So, but most of the time these are implicit assumptions being made by the designer of the system, designer of the explanation system. And there are a lot of advantages being more explicit about these assumptions, making the fact that, okay, the reason why I'm doing this is because the human has like no knowledge about the system, or humans reasoning is limited, and maybe giving examples that are similar to this is better. Even in the case-based system, maybe depending on the user type, maybe some examples may be better than others, right? So it might be even there, introducing explicit modeling about the humans' beliefs and systems could lead to better solutions. I'm not sure if the person who asked the question can maybe speak, but I would like to know what exactly the evolutionary rule-based recommendation approaches are, and maybe we can try to talk about how it connects to what we're talking about. But at least what I've seen is a lot of the XAI works are making these assumptions, but they're making it implicitly, and there is advantages to being more explicit about these assumptions. Yeah, does that make sense?